Okay. So we've looked at kinematics. We've reviewed what the different symbols mean, but there's really no new, listen please, there are no new equations. Really all we've done is we've converted all of our kinematics equations into angular versions of the same equations. So when an object moves in a circle, something must cause that. And the cause for circular motion, that for a revolving object, is centripetal force. And we mentioned this yesterday. Centripetal force is a center-seeking force. Okay? That is oftentimes confused with another term that sounds a lot like this. Yeah. And it's actually centrifugal force. So those are really similar terms. Centripetal versus centrifugal. And oftentimes I hear beginning physics students or I hear these two words sort of blended together. So it's like centrifugal, centrifugal. They're really, really different. This, centripetal, is the actual force that causes things to revolve in a circle. So it's a center-seeking force, and it causes revolving motion versus rotating, right? We'll do rotating next unit. Centrifugal force is not really a force. It's a misnomer. It was the name given to the inertia that a mass experiences as it moves in a circle.
So like the gravity from inertia, essentially?
Yeah, kind of. You can kind of think of it that way. Remember, inertia is like a tendency. So it doesn't cause motion, it's just the continuation of motion. So all the stuff that's sitting out right now that's not moving, it has inertia of rest. It'll just keep doing that. If I take that tennis ball and throw it across the room until it hits the back of the room or the ground, it'll keep moving. The same thing is true of inertia of circular motion. It's the tendency for an object to want to keep moving the way it was moving. And it's really not even circular, it's actually due to circular motion. We give it a special name. Really all this is just inertia of a moving object. Travis?
So if you were to draw the Earth and whatnot, the centrifugal force would be like perpendicular and with the rotation to the center-seeking force.
That is correct. I'll draw an example. Let's use something a little smaller than the Earth. Let's say that we have a car. We have a car traveling in a circle, like rounding a curve, okay? And we're looking at it from above. The center-seeking force would be pulling in which direction at this point? Point the direction that the center-seeking force. Good. Toward the center of the circle, which is toward the window, right?
Oh, I see.
Okay. When the car is right here at the top of this circle, in this particular picture, which way will the center-seeking force be acting?
Down toward the center.
Down toward the center of this circle, right? When the car is kind of at this spot right here, which way will the center-seeking force be acting?
Top left.
Yep.
West of north.
Yes.
I thought I wrote it down in my test.
Okay. And so they'll all be pointing toward the center of that circle, right? So those are all centripetal forces. And centripetal forces are usually caused by something else. Centripetal force is a way to describe the force that makes this happen. So what is the force that keeps the car in a circle, in other words, so it doesn't like fly off the road?
Centrifugal.
Somebody said it over here. What is it? Friction, correct. If there's not enough, how many of you are new drivers this winter? New, like this is your first winter? Arthur, your hand was up and then it was down. Okay.
I think it's the first.
How many of you, this is your second winter of driving?
I mean, this is
Wow,
the first
see?
time I drove a lot.
What, in middle-class white communities, we send our kids to school late. Seriously, 25 years ago, hardly anybody would have raised their hand because they were all a year younger than you as juniors. Yeah. Especially the boys. Woo. Don't send your 4-year-olds to kindergarten if they're boys, especially. Oh, that doesn't go well.
That poor woman who had to teach them.
Yeah. Peter.
So like as people sitting in the car turning right and like that's the centrifugal force that so are they always opposite those lines?
Yes. Yeah, we'll get to that. So this is friction, right, that holds the car in the center of the circle. For my drivers that drove last winter, if you're in this car, in this position, and there's not enough friction, this pink vector goes away, right? Let's say there's no friction. You hit a slippery spot on the road. Point in the direction that this car right here will travel.
It'll keep going straight.
Excellent.
And it won't stop until it gets.
Right. It keeps going straight. So you're in the car, you're trying to turn to the right, but and you keep going straight, right? Doesn't matter how hard you turn.
And your anti-lock brakes are useless.
This
The demon of winter laughs maniacally.
is centrifugal. Now, it's not exactly what it feels like, though. Peter was accurately actually describing that game that you played in the back seat.
When you
Is that what you called it?
I called it
Jello? Okay. So, all right. Who are the youngest siblings in the room? Okay. So if you're the youngest sibling, you're the victim of this game. Because what happens is, right, the car is turning to the right, you're in the family minivan, you're on the bench seat, and if you're on this side, there's an inevitable squishing of you, the youngest sibling, to the outside of the car, right? And your older siblings couldn't help themselves. Oh, I didn't do anything. Mom just took the turn, right? By the way, oldest sibling. Did it all the time.
If you do it just right, you can angle yourself on the door and actually push off as you're turning and just ram them at like 10 miles an hour.
Yeah.
It's wonderful.
All right. So which way, point in the direction, so you're in the car, which way does it feel like you're getting moved or squished? Yeah, to the door. Right, the opposite way that you're turning. So, it's not really like that, by the way, babies. What's really happening is the door is pushing this way on you. Does that make sense? So that's why, because you are the center of the universe, clearly, that's why it feels like you're going this way. Because in reality, if this pink vector go bye-bye, what do?
Go forward.
Woo, you go that way, you go straight forward, right? So it's not a real force. It's the same exact effect as the inertia you feel if you're accelerating from a stoplight or you slam on your brakes. So if you accelerate from a stoplight, so we're going to go toward the board, which way does it feel like you're moving? Feels like you're being lurched backwards. Are you really being pushed backwards?
No.
No, what's happening?
You're staying in the same spot and the car's moving forward.
Right. That's correct. You got it?
Essentially,
So centrifugal force is just what it feels like to you in the car. It's what the clothes feel when they're in the washing machine. If we weren't traveling in such a big circle here on the Earth, it's what we would feel like as we are flung in a big circle around the sun. But we also have gravity holding us to the ground, which tends to be a little bit stronger than the inertia. So we don't have to worry about being flung off the Earth, is what I'm saying. Okay?
So centrifugal force is just a force that scientists made up to explain the human perception of momentum that isn't actually there.
Exactly. Cool. Well done, sir. Little golf clap for Cosmo.
Near people.
Yeah.
What?
Say it in more plain talk.
Basically, centrifugal force is an observation that scientists made, and we're like, this is a force, but it's not. It's just a force in a term that we made up to explain something that we observed in the world that isn't actually reality.
Because
It's
we
a
perceive
fall-
our environment.
Exactly. It's a flaw of human perception.
She said
Yes, it is.
simplify it.
Hey, flaw, like
It's the
error,
matrix.
mistake, screw up, perception, how you see and feel things, human, people.
Figure it out.
All right.
I'm laying down.
You think there's any math here?
Yeah.
So of course there is. I'm actually, maybe tomorrow I'll derive this formula for you, but for right now, you're just gonna trust me, okay? All right, you can do that.
Are we gonna use centrifugal force
Centrifugal force, no, just conceptual. There's no math
Okay.
that goes with centrifugal force, it's just inertia.
Okay.
It's a way to describe how you feel.
Cause that'd be funny because
No.
that would mean it's
Yes.
So we're gonna find out like the amount of inertia.
Correct, right. It's a relative thing, so if you go faster, it'll feel like the centrifugal force is bigger. If you take the turn tighter, so you turn more sharply, it'll feel like the centrifugal force is bigger, but it's just how you perceive it. Okay, good question. All right, so centripetal force, I'm going to just go like this. If you derive what's happening to the car as it goes around in a circle or any object, you end up with this. Okay? That's centripetal force. And by the way, it's on the board in blue, right under F equals ma. So we've added that to our list of equations. Notice that I also have it's equal to m omega squared times r. That's just doing that angular to linear conversion. These are the exact same formula. This is just describing the centripetal force in linear velocity terms, so that would be meters per second. And here, it's in angular velocity terms, radians per second. Get it? Okay. If I use Newton's second law, F equals ma, and solve for acceleration, I end up dividing by mass, correct?
Yeah.
So what would I get if I take this equation and divide out the mass?
You'll get c squared.
V squared over r, and that's the way we write centripetal acceleration. Get rid of the mass, and you have just acceleration, okay? So those are the equations that we're going to use, and we will practice a bunch of times with that. So let's try a real-world example. We'll use our car going around in a circle with this centripetal force equation. Now, by the way, this works for any revolving object. So instead of this being a car, what if this were a planet? What would the pink vectors be represented by? Force due to gravity. If this were the Earth and that dot was the sun, it would be the gravity from
The song.
the sun's mass, correct. On Thursday, we're actually going to talk about Isaac Newton, who was like your age when he came up with his universal law of gravity, and we'll actually do the math for orbiting objects. But for right now, what is that pink vector? What is this pink vector?
Centripetal force.
It's centripetal, but what causes centripetal force in this case?
Gravity.
No, it's not gravity.
Friction.
Friction. That's friction.
Wait, so it'd be friction due to gravity for the sun?
No, but
No, it's just gravity. If this were the sun and this were the Earth, instead of F,
Is it like a different
Friction.
playing field in space because it's a vacuum and there's no gravity, like, there's no centered gravity, I guess?
I have no idea what you're asking me, Travis, I'm sorry.
If you just go to a random point in space,
Yeah.
there's no gravity. If you go to a random point on Earth, there will always be gravity. So is it like a different playing field in physics?
Yes, but the truth is there's always gravity in space, too.
I know, but
Okay,
theoretically.
okay, yes.
Okay.
Way out in deep space where you're not close enough to
Like,
any mass
yeah.
to really feel the effect, yes, that's correct. All right, so what we're going to do is we're going to combine this frictional force with centripetal force. So friction in this case is a centripetal force. And if this is a flat road, it'll just be mu times the normal, right? And that will be equal to mv squared over r. if it's a flat road, what expression do we use to represent the normal force? Mass times gravity. Good, thank you. Now, by the way, we bank turns, right, like for on-ramps to the highway, and we do that to, it kind of works with that whole inertia thing. If, think about the car moving in this clockwise circle, which way would the curve be banked? In other words, where would the high side of this curve be?
On the left.
On this side, on the left side of the car? That is correct. So I know you know intuitively why that works. The physics is actually pretty dang complicated because it has an impact on the normal force. So there's actually a triangle, and the normal force aids, sort of kind of pushes toward the center of the circle, so you get help from friction, and you get a little help from the road surface itself due to gravity. So we're not going to do, you'll do that next year when you take AP physics. Okay? It's a big, long, full one-page problem.
1 page.
1 page. Well, it depends on how big you write, I guess.
It sounds so small because you say 1 page.
Yeah.
What gets to go bye-bye now?
Page.
Math.
Yeah. So I've noticed friction is the centripetal force. And why is that good that mass go bye-bye?
Because that means that we
Those
can.
are variables.
We don't need
And
math.
not
Come on, talk to me in the real world. Why is it good that mass go bye-bye here?
because
Because
in
it's
civil
hard.
engineering, you wouldn't know like the mass of any given car. You wouldn't have like a specific one.
Right.
You have like semi-trucks and then you have like small little cars.
Exactly, yeah. So in the real world, it's nice not to have to worry about designing different roads for different mass cars, right?
Yeah.
Okay. So what this means is the things that affect how fast you can drive in a circle are the road conditions and your tire conditions. That's what mu happens to be, right? How sticky is the road? What planet you're on?
Generally.
And how sharp the curve. Okay? That's what determines how fast. And you ever notice that there are like guidelines, speed guidelines when you round a sharp curve?
Yep.
You can always go faster than that, right?
Yeah, exactly.
Like 10.
You just floor it. Excellent. All right. Why do you think those tend to be lower than what is fairly safe?
So if you go over it, you can't sue them and be like, oh, you
I was
recommended
going
I went
sure.
45 miles and I went 45 and I still died. So, ah,
So I'm gonna
Yes.
from the grave.
Yes, absolutely. It covers liability. What else? Go ahead, Sarah. Yes. Well done. Yeah. Do we know does every engineer know exactly what mu is for every single car?
No.
No, and it's different based on the age of the tires. Absolutely. Nice.
In the
Good.
road when it decays.
I think that's extra credit worthy, by the way. What else? Oh, see? Nice adjustment on the fly, Varun. Did anyone else catch that?
I did.
More people in the car, never mind, math canceled. Nice. What else could affect mu besides the tire? Road conditions. That's kind of what we're solving for, Shab. True, Varun. Varun said gravity's different on different places of the Earth. That is true, but we're not going to go to Mount Everest, so it's probably not going to have a big impact. But yeah, it has to do with coefficient of friction. There's something that's not in this equation too, by the way. Even though mass, tire pressure, even though mass is not a critical component in this equation, obviously it cancels. There are things that are not in this equation, like the length of the wheelbase and the center of gravity of the car. And that's like a little internal torque problem for each individual car. So although we don't have to worry about the mass, engineers do take into account sort of the most poorly designed cars. Those cars with a really short wheelbase and a really high center of gravity, and they're much more likely to tip over.
So Mini Coopers.
Yeah, what were like Jeeps are a good example of a high center of gravity, short wheelbase.
Tiny and compact, but super tall
Right,
nonetheless.
right, and that's bad. That's a bad combination. Let's put numbers in here and see, like reasonable numbers, and see what we get.
Okay.
Let's solve for the velocity of the car. Okay? See where that came from? And I'll put in some typical numbers. On a dry road, about let's say 2.5 from you. That's pretty typical. Dry road, decent tread. Radius of the turn, let's say, is 100 feet. That's actually a pretty tight turn, to be honest, on a road, a flat road. And gravity, since I'm in feet, what value do I have to use for gravity? 32 feet per second squared. So if I plug those into my calculator, 0.25 times 100 times 2 square root is 28 feet per second, because we're in feet and seconds, right? Feet squared, second squared, square root, so 28 feet per second. And let's make this meaningful. So let's do miles per hour, right?
Oh dear.
5 tomato feet in 1 mile. And how many seconds in an hour? Yeah, good. So the velocity in miles per hour is going to be about a little under 20, 19 miles an hour. It's actually a pretty tight turn. 100 feet is not a very big radius. Yeah. So there we go. Okay. So that's the math we're going to do starting tomorrow.